Somewhere on this planet right now, the day side sits close to 2700 Kelvin, nearly 4400 degrees Fahrenheit, hot enough that rock does not stay solid. It flows, and it has been flowing for longer than this solar system has existed. This is not a hypothetical world built to make a point. It is a real measured place, and you are about to find out exactly what happens if you stand on it. This is 55 Cancri e, a super-Earth roughly 41 light-years from here. NASA's own exoplanet catalog describes it in one blunt line. This super-hot world is covered in a global ocean of lava and has sparkling skies. You are about to spend the next several minutes learning exactly the first second standing there is that your body would never register a single detail that follows this one. Start with what kind of world it actually is. Astronomers confirmed 55 Cancri e in 2004, found the way most of the first generation of exoplanets were found, not by seeing it directly, but by watching its star wobble, tugged by the gravity of something unseen. NASA's own catalog lists the planet at roughly 8 Earth masses and just under twice Earth's width, a size class astronomers call a super-Earth. It is heavier and wider than anything rocky in our own solar system, and there is nothing quite like it sitting nearby. That detection method matters more than it sounds like it should. Astronomers were not staring at a point of light and watching a planet cross in front of it. They were staring at the star itself, waiting for a rhythmic, almost imperceptible shift in its own light, caused by the gravitational pull of something they would never see directly. 55 Cancri e was confirmed the same way most of that first generation of exoplanets was confirmed, years before any instrument existed that was sensitive enough to look at a planetary atmosphere directly. Everything you are about to hear about lava, heat, and gas came later, built on top of a discovery that started as nothing more than a wobble buried in a distant star's spectrum. Now ask the obvious question, why is a rocky planet not a gas giant running hot enough to keep stone in a liquid state? The answer is distance, and the number involved is almost absurd. According to NASA, this planet whips around its star every 18 hours. Mercury, the innermost planet in our own solar system, takes about 88 days to complete one orbit. 55 Cancri e finishes an entire year in less time than it takes you to sleep for 3 nights. That because of the planet's proximity to the star, it is tidally locked by gravity just as our moon is to Earth. One side always faces the star, the other side never does. There is no sunrise here, no sunset, no day that ends, just 2 permanent hemispheres, one burning and one dark, locked in place for as long as the planet exists. NASA's own description of what that produces is direct. One side of the planet, the day side, is always cooking under the intense heat of its star, while the night side remains in the dark and is much cooler. Always is doing real work in that sentence. For as long as this system has existed. In 2016, a team led by Brice-Olivier Demory of the University of Cambridge pointed NASA's Spitzer Space Telescope at this planet for a total of 80 hours, watching it orbit its star again and again to build the first real thermal map of its surface. What they found, published in the journal Nature, was a temperature swing of about 2,340 degrees Fahrenheit between the 2 hemispheres. The hottest side reached nearly 4,400 degrees Fahrenheit, roughly 2,700 Kelvin. The coolest side still 1,400 Kelvin. Read that again. The cool side of this planet is still hot enough to keep most metals in a liquid state. There is no cold side here, there is only less catastrophic. Hold those numbers loosely, because they are the best current measurement from one well-studied dataset, not a final word carved in stone. Different observing campaigns across the years since have produced day-side estimates that shift depending on the wavelength studied and the exact orbital phase captured, and researchers studying this planet have been candid that the exact figure is a moving target, refined a little further with each new instrument point. Decade of repeated measurement is the basic shape of the finding, an enormous, stable gap between a side that is merely scorching and a side that is far worse. This is where the picture stops being abstract. Michael Gillen, an astronomer at the University of Liège in Belgium who worked on the same study, described what the surface itself might actually look like. The day side could possibly have rivers of lava and big pools of extremely hot magma, while the night side would likely have solidified lava flows like those found in Hawaii. Rivers of molten rock on one side, frozen black stone on the other. And between the two, researchers found the heat transfer was inefficient, too weak to even out the hemispheres, the kind of imbalance you would expect either from a planet with little or no atmosphere to carry that heat around, or from an ocean of exposed magma simply radiating its heat straight into space instead of sharing it. Now hold that image and ask the only question that actually matters if you were the one standing there. What happens in the first second? Nothing dramatic in the sense of a countdown or a warning. There would not be time for one. At close to 2,000 let alone survives contact. Steel liquefies well below that point, so does nearly every rock you have ever touched on the surface of Earth. Whatever passes for air on this planet's day side would already be an incinerating wind before it ever reached a lung, if a lung could exist there at all, which it could not. This is not a place where danger builds gradually across a scene. The scene is already finished before it starts. Cross to the night side at around 1400 Kelvin and the outcome does not change. It only takes slightly longer to arrive at the same ending. There is one that did not exist when Demory's team first mapped its heat. In 2024, a team led by Renyu Hu at NASA's Jet Propulsion Laboratory pointed the James Webb Space Telescope at 55 Cancri E and found something the Spitzer data alone could never show: signs of an atmosphere. The Webb data suggested a thin shell of gas, possibly rich in carbon dioxide or carbon monoxide, wrapped around this furnace of a planet. According to Hu's team, this would be a secondary atmosphere that is continuously replenished by the magma ocean, because magma is not just crystals and liquid rock. There's a lot of dissolved gas in it too. The lava ocean is not simply sitting there being hot. It may be actively breathing, releasing gas from its own molten interior fast enough to keep replacing an atmosphere that starlight and radiation are simultaneously trying to strip away. Even NASA's own catalog entry leaves one detail dangling. Sparkling skies is the phrase used, without further explanation on that page, and it is a fair description of an atmosphere nobody has fully mapped yet. Whatever combination of vaporized minerals, dissolved gas, and starlight produces that visual effect from a comfortable distance, nobody standing beneath it would ever call it sparkling. That word belongs entirely to an observer light years away, reading a spectrum through a cold telescope mirror, not to anything or anyone that could ever survive underneath it. Sit with what that means. This is not a dead world slowly cooling towards some quiet equilibrium. It is a planet locked into a permanent active cycle, heat driving gas out of liquid rock, radiation trying to tear that gas back off the surface, the whole exchange repeating without pause because nothing here ever gets a night to recover, and nothing here ever gets a day to end. Here's the part worth carrying with you after this episode is over. 55 Cancri E is not some edge case scraped from the bottom of the exoplanet catalog. It is one of the closest, most observed rocky planets we have ever found, precisely because its short orbit and bright, nearby star make it easy to study again and again. Astronomers did not have to search hard to find a world this extreme. It was sitting in our own galactic backyard the entire time. 3 separate instruments across 3 different decades have now looked at this single point of light, and every result has landed in the same direction: hotter before it suggested. Compare that to where you're sitting right now. Earth also faces its own star every single day, and yet nothing about your morning has ever demanded a word like furnace. That difference is not because Earth is special in any cosmic sense. It is because Earth spins, because it orbits a much calmer star at a far more forgiving distance, and because no hemisphere of this planet has ever been asked to face constant daylight without once looking away. Move a rocky planet close enough to nearly any star, lock its rotation the way gravity locked this one, and a lava ocean stops being an anomaly. It becomes the expected outcome of ordinary physics, applied without mercy, to a world unlucky enough to sit in the wrong orbit. That should change how you think about the planets nobody has looked at nearly this closely yet. So here's the honest question for the comments. One of the very first rocky exoplanets ever confirmed turned out to be an active, gas-breathing ocean of lava, hiding in plain sight 41 light-years away. Does that make you more curious about the thousands of other planets NASA has now confirmed but barely characterized? Or does it make the sheer scale of what is still unmeasured feel more overwhelming than exciting? There's no wrong answer, and the 2 reactions are not as different as they sound. We spent this episode on a world violent enough to end you before you finished a single breath. Next time we go looking for something quieter and somehow far more violent still. An event that released more energy in a fraction of a second than our sun will produce across its entire lifetime. And that happened in near total silence, without a flash bright enough for any eye to have ever caught it. You just watched a planet breathe fire from the inside out. Next time you find out what it sounds like when 2 dead stars finally collide.